Hello, everyone. My name is Emelie Siderud, and I'm a PhD student at Uppsala University. And I will talk about a recently started and ongoing project that I'm working on together with my supervisors. So I'll be presenting sort of first results from this work, where we are investigating how stellar pulsations affect the mass loss of AGB stars. And we're doing this by, as Arif mentioned, by implementing results from their 3D models to our 1D radiation hydrodynamical code. So I will start by giving an overview of the modeling method that we're using. So we're using a code called Darwin, which is a 1D radiation hydrodynamical code that simulates the winds of AGB stars. So the starting point is a spherically symmetric star with a compact hydrostatic atmosphere. And the inner boundary of the model is situated just below the photosphere. And stellar pulsations are simulated by sinusoidal variations of the radius and luminosity at this inner boundary, which is defined then by a pulsation period and a velocity amplitude and a luminosity amplitude. So as the pulsations are gradually ramped up, the initially compact hydrostatic atmosphere turns into an extended dynamical atmosphere that includes complex physical processes such as the propagation of shock waves and the formation and destruction of dust. So if a wind develops, the outer boundary, which initially is located close to the star, will follow the outflow up to a point where it has reached its terminal velocity. And this is typically the case around 25 stellar radii. So each model is defined by a set of stellar parameters such as effective temperature, luminosity, and current stellar mass, and also chemical composition or the elemental abundances. So in this work, we're looking at oxygen-rich AGB stars or M-type AGB stars. So as I mentioned in the previous slide, the pulsation properties are defined by a pulsation period, by a velocity and luminosity amplitude, and I will get back to this on the next slide. Another input is the microphysical properties of gas and dust. So the output consists of radial structures of gas and dust, which means that the mass loss rates, wind velocities, and dust properties, such as grain abundances and grain sizes, are direct results of the simulations. So as you all know, stellar pulsations play a crucial role for the mass loss of AGB stars by triggering shock waves in the stellar atmospheres, which then lift gas to distances where dust can condense. And the timing of these pulsations here is very important in terms of when the dust forms in the pulsation cycle. So this may result in that the dust falls back to the star, or that it's pushed outwards from the radiation pressure. So in the Darwin models, the effects of the pulsation on the atmosphere and wind are simulated by prescribing temporal variations of the gas velocity and luminosity at the inner boundary of these models. Yes, okay. And if we look at what we have been using previously in the Darwin models, or what's always been used, I think, is this period luminosity relation. So this means that the period is derived directly from the luminosity, and this is a relation that is derived from observed stars. So in this figure from Arif's recent paper, these or the solid line and the dot dashed line. Let's see if I, okay. Yeah. here represents two such relations. And the red symbols represents or corresponds to the observations that were used to derive these relations. And although there is a sort of general trend, we can also see that there's a relatively large scatter in some areas. So where one period could actually represent several luminosities, for example. So another relation is then the period mean density relation, which was explored by Riff and collaborators. So in this figure, the circles and squares represent their models. And as you can see, they represent a sort of realistic scatter of real AGB stars. And from these models, they have derived a relation based on these models. So what we have done now is to implement both of these period relations and see how that affects the output of our models. So first, let's have a further look at these different pulsation periods. So here we have the period luminosity relation for different stellar parameters. So we have temperature on the x-axis and luminosity on the y-axis, and the color represents a different period in days. And as expected, with higher luminosity, we get higher or longer periods. Now for the mean density relation, it looks a little bit different. So now we have the highest pulsation periods in the upper right corner, so at low temperatures and high luminosities. And then it's the periods are getting shorter in a sort of diagonal direction. And I should also note that we have looked at a 2 solar mass model for this project for now. So that is what the focus is on right now. So here I'm comparing the two relations by plotting the ratio between the different periods. And I will also divide these into squares that represents the different input parameters that we use in our models. So the temperatures have a step of about 100 Kelvin, and the luminosity have a step of log 0.15. So from this plot, we can see that this is a sort of approximately where the models or the periods are the same in both relations. So where it's close to 1. So that means to the right of this line, we have longer periods with the 3D periods, and to the left of the line, we have shorter periods with the 3D derived periods. So, but we're not looking at all of these stellar parameters because they're not all relevant for a 2 solar mass star. So we're looking at these selected grid of models, and this is based on the M-type grid presented by Sarah Blad et al. 2019 from their paper. And so what we can see is that in this model grid, all the models will have shorter periods with the 3D period compared to the luminosity period. So now we're interested in seeing what this will do to the result of our wind models. So this is a wind map where we plot, which stellar parameters results in winds and not. So for each temperature and luminosity combination, we also have 3 different piston velocities, you can see here. So this gives us sort of a boundary between wind and no wind in terms of these stellar parameters. So if we look at this plot, we have the new models with the 3D periods. And so here you can see that we get more models with winds. So these diamonds represent the differences between these two plots. So we get more wind at higher temperatures and higher luminosities than before when we implement these shorter periods. So we can also have a look at the mass loss rates. So here, the color is in log of the mass loss rate. And it's difficult to compare them, but I will also show a ratio later. But we can see that they, more or less span the same area, so there are no major differences there. And you can also see that along the sort of no-wind boundaries, where we have slightly lower mass loss rates typically. You can also have a look at wind velocities. And again, we have a sort of similar spread among different velocities, so it might be a little bit difficult to see on this plot, but instead here I have plotted the ratios between the two types of models, so the 3D period over the luminosity period, and here we can see that the models that are sort of closest to this no-wind boundaries is where we see the largest difference. So we have much higher mass loss rates in the 3D period models compared to the luminosity period ones. But other than that, there's seems to be quite similar behavior. Yeah, so no clear trend here in the wind velocities, but we can see that there are some differences and some similarities. So instead, we can have a look at this plot and compare it to some observations. So we have the wind velocity on the x-axis and the mass loss rate on the y-axis, and the pluses represent Miras and the x's semi-regular stars. And this is observations by Olofsson et al. 2002 and González Delgado et al. 2003. So now these purple circles are the luminosity period relation. And if we now plot the 3D models, we can see that they end up in sort of the same area. We get similar maximum and minimum velocities and mass loss rates. And if we can also link each model to the corresponding model in both grids. So we can see that there's no clear trend between the models. Yeah. And we see that the new wind models in the 3D grid, so the ones that are at the higher luminosities and higher temperatures, seem to end up in this region here and some over there. So I think, yeah, so the sort of main conclusion or takeaway from this talk is that with the shorter periods, we seem to get models with higher temperatures and luminosities that result in winds. But as I mentioned, this is a sort of recently started project and it's ongoing, so there's a lot of work to still be done. So we're looking to first extend the grid with more models, and then also to use further input from the 3D models that we've talked about previously before the break. And that's it. Thank you.
Thank you. Thank you, Emelie. Are there questions? In the meantime, I have one. I have noticed, Emelie, that in the wind velocity, if I'm not wrong, is the highest velocity is not reached when you have the highest density, highest mass loss rate, isn't it? If we can go back to the grid.
Yep. You mean, oops.
As I would expect that the coolest and would have been also the faster. Well, I see that yes, with the highest pulsation. Well, if you have a comment on this or.
Sorry, can you say again?
that I would expect the highest velocity would have been reached in the most extreme temperature, and also pulsation. And
But what do you mean with most extreme temperatures?
well, the coolest one, but
the coolest, yeah. But isn't that
yes, we are. I mean, for example, in the right side of the panel is, I mean, is a matter of the pulsation that we are assuming. No, that's not that clear trend.
Yeah, no, you're right. It looks a bit clearer here, I think. That's true. Yeah, it's an interesting point, actually. Maybe something to look into a bit more, actually.
Okay.
Thank you.
Are there comments or questions? Thaisa?
I just wonder if you have an explanation for, in observations, some of the highest mass loss rate stars also have the longest periods, right? Which I think is not what you said.
Let's see. Yeah, no, right. Yeah, that's a good point. Well, but no, I think if we look at this plot, the highest periods are sort of, at the lowest temperatures, which also corresponds to the highest mass loss rates, I think. What it looks like, or I'm not sure if I understood the question.
No, okay, thank you. I think I misheard. Sorry.
Okay. Okay.
Are there other?
I think maybe the ratios differ the most at this boundary. Maybe that's what confused me. But okay.